I just want to say hi to everyone that can attend the virtual lubrication conference, summit, I should say. It's good morning, good afternoon, and good evening to all. Um, my talk today will be on heat treatment of membrane patch for wear particle analysis, which is interesting in itself, utilizing the technology of fluorography to be able to bridge it towards the membrane patch, which Greg Livingstone has been involved with for doing his MPC testing. So what I've done here in the second slide is show you a definition out of Wikipedia for fluorography, and then I saw some definitions in different websites for the membrane patch. And what I did was combine these techniques together based on the fact that we were able to find a glass membrane filter that can withstand some of the heat treatment aspect. And I'm going to explain the basics of what's going on. Typically, this is just a process of what we're doing in regards to the membrane patch, utilizing the technology of fluorography itself. Okay. Here's what you see in fluorography. We use a magnet, a neodymium magnet that's very powerful, up to about 3,800 Gauss. And what that does, it helps separate the ferrous wear debris, and the flow rate across that magnet on a substrate is slow enough so that also the ferrous wear debris can be precipitated onto the substrate itself. The other two photos are two different ways of possibly getting a membrane patch. One using a vacuum pump, and the other one is using basically a vacuum pump to electrical vacuum pump to suck the samples through the filter membrane patch. So some people may say, well, if you haven't got involved with this technology and condition monitoring, what is wear? And typically it's the loss of debris coming from the mating portions of the machine components themselves. What happens is we have different classifications of the type of debris we see, different wear mechanisms that create the wear debris that we have. So what I've been trying to do is categorize these things into not just wear mechanisms, but also into particle classifications. And you'll see what I mean in the next few slides coming up. In order to basically separate out the debris in fluorography, what we do is we typically use a qualitative analysis device called the ferrogram maker. And all it does is basically pump the lubricant with a wash solution over the slide, and basically the slide is then, the oil comes down from the entry to the exit, and then at the exit, it's sucked off using a small vacuum. Once the oil is passed, then there is a wash solution that basically washes the residue of the oil. And what it entails is we get to create basically a slide like this. Now what happens here is you'll notice at the entry point, the largest ferrous wear debris would line up in strings because we have the magnet assembly basically separates the north and the south. And what happens is you're developing what we call magnetic lines of definition. And these particles, if they're ferrous, will line up like the magnetic strings. Now what happens is if it's non-magnetic or non-metallic, what will happen is you'll see a random deposits of debris, especially in the area over here, like in this particular non-ferrous debris or non-metallic debris, depending on if the light gets blocked or the basically the light can penetrate through. We can tell whether it's metal or non-metal. These are just some of the different techniques that we uncovered in fluorography. However, in using the patch test, we can't use all of those different techniques, but we can use some. Okay. The next step is how do we classify these things in? And what I've done is I basically separate these classifications out to three specific areas that we can generically use. One is non-ferrous, which you can see copper, aluminum, babbitt, zinc, different other metals that are out there in the world of our industrial environment. Mostly there's a ferrous, which is magnetic, Fe2O3, Fe3O4, stainless. These will line up in the lines of the magnetic field. And then there's contaminants, and that's typically basically the other stuff that doesn't fit the other two categories: dust, dirt, manufacturing debris, organic materials such as filters. All those different things basically lie in the world of contaminants. So, in having these three classifications, it's in the world of diagnosis, I can easily point each classification towards a specific, maybe towards a specific application. Like for instance, if I see a lot of non-ferrous application, I might point towards, say, a bearing problem that's going on. If I see a lot of ferrous application, and I might say, hey, it might be coming from, say, a lot of gearbox where I have a lot of stress and loads that's going on. If I see a contaminant situation, then I'm looking at possibly external activity going on in this oil, the breather, all these different things that can affect the operating process of the components themselves. The next slide typically looks at our two different microscopes. One on the left is a stereoscope, which can be used for the patch test, which has magnification up to about 200 to 300x or 300x magnification. Basically a 20x lens with a 10x eyepiece, and has typically a zoom. Basically, you can have a zoom effect that can basically bring the image in and out of what components you might be looking at. The other microscope is typically the one we use for the ferrography, and that is the ferroscope, which has a lighting from the top and lighting from the bottom. That's why the ferrogram is made of glass. This way we can see through the substrate, and we can see coming from the top of the substrate. Whereas the stereoscope, I can only see from the top because the membrane or the filter is basically non-translucent. So this helps us to help identify different material, and also help identify metal from non-metal very easily. But we can go beyond that with the test on looking at some of the debris in the membrane patch. Let me show you some examples using the ferrography, having a 3D microscope and so forth. Those are all the niceties of the looking at the wear debris. This one shows particles that's been heat treated. Now, this is a key element of what the whole presentation is all about. This by heat treating your wear debris in a ferrography application, I can tell if certain wear metals have been oxidized to a certain color based on using the heat treatment application that we provide. For instance, this particular photo, all the metal was white, silverous color. After heat treatment in the first stage, some particles turn blue, some turn bronze color. Basically, the blue is indicating low alloy steel, and the bronze color is indicating medium alloy steel. This is all stemming from, say, a gearbox that may be a case hardened surfaces. And what happens is the case hardened surfaces look like medium alloy steel. And when the wear debris, basically, or the scuffing marks on the gears are beyond the case hardened surfaces, that's when the low alloy metal starts to be created. And you'll notice some of these things have these striation lines sometimes on these particles. That's when we know how the gears are not the gearbox is not working the way it's supposed to work. Now, how does this happen? What we do is we utilize this hot plate, and you can see we have a surface thermometer on there. And one of the things that one of my colleagues, Russ Lodi, who helped put this whole thing together, was enable us to get the substrate onto the hot plate at a certain temperature stage for 90 seconds. This basically oxidizes the surface structure of the particles to a certain color at certain periods of time. And then what happens then is we can then go back to that wear debris that we took prior to heat treating, and then after heat treating, we locate the same wear debris, and we see what the color change then occurs, and that will help us to diagnose exactly what's going on with that particular piece of machinery. Okay, so how we do that, there's again, is what we utilize. The ferroscope, which has the two light sources for the ferrogram, And then we have the stereoscope, which has the one light source for the patch test. Now, I don't know how many people know about the patch test or not, but it is an ASTM standard. I don't have it off the top of my head, but what I'm going to do is I've written this amendment to possibly be attached to the ASTM standard. And what I'm going to do is utilize what all that's been out there to be applied to the standard itself, saying they can utilize a glass membrane filter to be able to look at other or diagnose other particular material that might be on the patch itself. Here's one from a reputable company, and showing you they have a kit with all the containers of the glass patch and everything, tweezers, vacuum pumps, tubing, holders for the filter, and so forth. One of the colleagues that I think was from the Canadian, Australian military, Air Force, they applied some photos and they gave me some photos which they presented in an ASTM presentation, and they showed how they were looking to get patches, making the samples on doing the funnel and so forth. So my time is looking okay. This is, like I said, is some of the procedures that's involved, and ASTM has these procedures that you can go through. Many people have different types of process or in terms of getting the patch themselves. Even Fluid has their own way of presenting the generic stuff and then being able to provide the patch that's needed for their MPC testing applications. So when I was asked to be involved with this, what I did was I basically chose a subject that I think can bridge from fluorography over to the membrane patch test. And what I did was I chose some photos that can give you an idea of what's going on there. Making the filter patch, putting it into a container, keeping everything clean, all the different things that basically amounts to making sure you're not cross-contaminating what's going on, because the information is very vital to what you see going on with your components themselves. In this particular case, they're looking at aircraft, helicopters, and a few other jet engines and so forth. Here's courtesy of Fluid and another company in regards to the different filter patch tests using a membrane vacuum pump and so forth. The other thing is I was able to at least incorporate the membrane patch. And when we start heat treating the patches, and I'll show you what those items are, we could possibly do a lot of other things other than just heat treat the patch to see what wear metals are. We can possibly do heat treating the patch to see if these colors change, and then that might reinforce what might be the diagnosing for this particular the test that's going on. So we might collaborate with Greg and his guys and so forth, and basically see what we can possibly do in that direction. Other than that, typically it's a 47 millimeter type device. There's also a 25 millimeter device patch that can be out there. One of the things I don't like, I should say, is there's no, it's hard to identify the same particle in the same area if you don't cross-reference where the location might be. And one of the things about the stereoscope, it doesn't give you a location area. So you may have to use a magic marker. You may have to use splitting up the patch into 4 quadrants, a quadrant of 1, 2, 3, 4, or north, south, east, and west. Those are some of the things that are tidbits that I'd like to pass on so that you can enable yourself to be able to pinpoint what's going on with the same particle of the that you're heat treating. Okay. Now, there are different what I call stages in heat treatment. There is a technical paper that was written way back in the 70s that illustrate and the technology today that can still be utilized, where they have 4 stages of heat treatment. Typically in the fluorography world, we only use stage 1. We don't typically go up to 400 degrees or 480 degrees C. We just stay right at 330 degrees C, which is amounts about 625 degrees Fahrenheit. And what happens there is it's giving you some insight on, say, 5200 steel turns to a blue color, carbon steel turns to a straw bronze, nickel doesn't change, Stainless steel doesn't change, so it's an organic can vaporize or char, and non-ferrous typically has no change unless it's like a Babbitt material, and then it tends to melt because the Babbitt material like tin and lead and zinc and so forth, they have a lower melting point than the other metals that you just saw here. So what I'd like to do is, I've got about 8 to 10 slides, and I've got about, I'd say 6 minutes or 4 minutes. I'm going to be zipping through the next 5 or 6 slides very quickly. So bear with me a second, okay? This one's one of the most important ones, which shows the photograph of before and after, as you can see. And this showing you low alloy steel, case hardened steel, different things that will indicate what type of diagnosis you're coming up with in regards to the heat treatment of this particular these slides, okay? Here are the patch themselves that I was able to buy. I shouldn't say buy, they basically provided to me because I gave them the information about what I'm trying to accomplish, and they saw that I was trying to get an ASTM amendment. They were ready and anxious to get me that information to move this forward. So I've already working with our WARE group in the ASTM CS96-6 group to be able to implement this type of thing as an amendment, opening up a work item. So these are just some of the glass membranes that I'm using. And then these are some of the wear debris that I was able to photograph off the glass membranes themselves. On the pictures on the left is before heat treatment, and it was known to be a Babbitt metal. And then after heat treatment, as you can see, it changed the shape because of the low melting point of the material. Here's another one, similar type situation, showing Babbitt before and after and what's going on. In this next slide, you'll see 2 other membrane filters that show you before and after. And you can see it's not that easy to distinguish what's going on. The background can interfere. Some of it can, depending on what type of membrane patch you have, things can get a little bit more burnt and on the patch itself. Some of them react, some of them don't. But you can see the before and the after is right here. The before and the after. And these are abrasive wear material, or as we know, cutting wear material that goes on, okay? Here is just some severe sliding wear from photography as an example of being able to see the background because you can see through the slide itself. So I'm just giving you some cross reference of what's going on. And then what I did in the case of what's going on here is we both used the photography and the membrane patch to pinpoint what this problem was in this particular plant down in the Texas area. So I just want to make sure that I gave a synopsis of being able to at least indicate what's going on and how you can utilize this towards a condition monitoring type situation. So I think I have I'm at the 19-minute mark. Here's some red oxides. I didn't get the chance to, we're experimenting to see if we can see those on a membrane patch. Right now, we can only see the severe wear metals at this point, not the oxides at this point, because they blend so much into the background of the patch themselves. So what I want to do is be able to figure out some lighting techniques to be able to hone in on those type of situations. Here's what those red oxides tend to point to, some sort of fretting corrosion type situation that we had saw, okay? With that being in mind, I'm up in my 20-minute presentation.